Good evening, everyone. From understanding the science of light to developing technologies that protect, connect, and empower our world, every great innovation begins with that one simple spark curiosity. With that spirit, I warmly welcome you all to the STOT Selection 19, proudly presented by the Kalams Institute of Youth Excellence, the KIYE Foundation. A very warm welcome to our respected mentors, faculty members, researchers, students, and young innovators, and everyone joining us live from different parts of our country. I'm your host, Rahitya, and I'm truly delighted to be with you this evening. It's a pleasure to host today's session, and I hope all of us leave with new ideas, inspiration, and deeper love for science and technology. Before we begin, let's make this today's session a little more interactive. So please drop your name, your college or city in the live chat. We would love to know where everyone is joining us from today. To everyone watching live, welcome once again. No matter where we are today, we are all connected by that one common purpose to learn, innovate, and to serve our nation through science and technology. Inspired by the vision of our beloved Kalam, the KIY Foundation believes in that one simple idea. Classroom gives us knowledge, yes, but learning from great scientists gives us the vision. KIY is actually a non-profit organization dedicated to connecting the students with scientists, researchers, and industry experts, helping bridge the gap between classroom learning and real-world innovation. Through meaningful interactions, expert lectures, students get the opportunity to learn directly from people who are actually shaping the future of science, engineering, aerospace, defense, and deep technology. And that is exactly why STOCS was also started. Here, the S stands for the space, science, aerospace, and future technologies. STOCS is more than just a lecture series. It is a national learning movement built on that one powerful idea. 52 weeks, 52 experts, 52 topics, 52 hours of learning and inspiration. A journey to learn, connect, inspire, and grow. Today's session actually takes us into one of the most exciting fields of modern science and technology. Every time we make a video call, use high-speed internet, or send information through optical fibers, or hear about advanced laser technologies, we are witnessing the power of photonics and optical science. These technologies are not only transforming communication and healthcare, but also playing a major role in space research, defense system, artificial intelligence, and the next generation engineering. As India moves towards becoming a technological driven and self-reliant nation, a Atmanirbhar Bharat, innovation in these areas are becoming more important than ever. Today's session is a wonderful opportunity to learn from someone who has spent years working on these advanced technologies and contributing to world-class research. If you are excited to learn something new today, type Jai Hind in the live chat right now. Before we introduce today's distinguished speaker, let's take a quick look at the vision and journey of the KIY Foundation. So I request our technical team to play the official audiovisual presentation. thank you. I hope that video inspired you as much as it inspired all of us. If you enjoyed it, please drop a message in the live chat. And we all believe that one of the best ways to understand the impact of this platform is by hearing directly from someone who has actually experienced it. So now I would like to invite our student coordinator, Rupang, to briefly share his journey with the KIYE Foundation. Rupang, the virtual stage is all yours.
Good evening to everyone. My name is Rupang. I'm very happy to share my experience with KIYE Foundation. When I joined KIYE as a volunteer, I thought it would be like any other college activities. But after working on events like Space Convention and Exam Vibo, I realized KIYE is much more than that. It gives students real responsibility, where I learned by communicating, coordinating, and working together. Before I joined KIYE, I was not very comfortable talking to new people or taking responsibility in a team. But with every event, my confidence grew. I become more open and learned to work with different people. I started stepping out of my comfort zone. Every event gave me a new responsibility to learn something and improve myself. As a AMS student, I always believed technical skills were enough, but KY changed my perspective. Meeting scientists, professionals, and students from different colleges taught me that communication, teamwork, leadership, and confidence are just as important. These are the skills that help me use my technical skills efficiently in the real world. One thing I really appreciate about KY is that it gives students opportunity to learn through experience, not just by listening or watching. Every responsibility, whether it's big or small, has helped me become a better version of myself. I'm also truly grateful for the guidance of mentors like Dr. G. Satish Reddy sir and Naresh Indian sir. Their encouragement motivated me to believe in my own potential and keep improving. I would like to say to every student that do not hesitate to take the first step. KY gave me the experience that helped me grow not just as a student but as a person. These lessons stay with me throughout my career. I hope more students get the opportunity to be the KY because it helps us grow in a way that goes beyond academic. I am truly thankful for the journey and everything has taught me. Thank you.
Thank you so much, Rupang, for sharing your inspiring journey with all of us. Your experience really reminds us how platforms like KIY can actually shape students' confidence, knowledge, and future. And now, everyone, it is the time for the most awaited part of today's session. It is my great honor to introduce our distinguished guest speaker, Dr. Nithyanandan Kanagaraj Garu, Assistant Professor in the Department of Physics at the IIT Hyderabad. Dr. Kanagaraj completed his PhD from the Pondicherry University and has conducted research in India as well as in the United Kingdom, France, and the Czech Republic. His work focuses on the photonics, fiber optics, ultra-fast lasers, and artificial intelligence in photonics. He has published more than 140 international research papers, holds several patents, and has collaborated with global companies like Thales and UIV. His achievements have earned him prestigious honors, including the SPIE, Laser Technology and Engineering Scholarship, and CNRS Postdoctoral Fellowship, and many more. We are truly honored to have him with us today to share his knowledge and experience. So, everyone watching, let's give our respected guest speaker a very warm virtual welcome. By filling the live chat, we'll welcome Sir Jai Hind or emoji. So, welcome, sir. Sir, thank you once again for accepting our invitation and spending your valuable time with us. We are all excited to learn from your experience, your research journey, and your thoughts on the future of photonics and advanced technologies. Without taking any more of time, the virtual stage is all yours, sir.
Thank you so much. So I'm so happy to be here, and thank you very much, Nageshji, for a very pleasantly surprised invitation, and just last day. Okay, so it was a too short notice for me to prepare a presentation, but the platform actually excited me that I should do something for this particular foundation. So I have been hearing quite a lot about this foundation for quite some time, and I've been following this foundation also. And today, Nageshji, I had the opportunity to talk to him also. So he has briefed what many different kind of activities the foundation is doing. This is fantastic, and this is what a country. These sorts of things is what as a country we require. You know, we have to empower our youth. This is the most important. India is considered to be one of the young country because we have a lot of young population, and we have to empower this young population if you want to see the country become a developed country in the near future. I think, and I'm sure this KIYE Foundation is doing a wonderful job, and I'm very honored to be here to give a talk. And this talk will be on photonics, but I was also told the audience will be quite vast, starting from school to engineers to a senior scientists as well as retired scientists. So I just don't want to disappoint anybody for that matter. So I just planned this presentation such a way that everybody have food for thoughts, which means that the people who are from schools will have something to take away, and people who are in an advanced stage, be it a scientist or retired scientist, they will also have something to learn and share about. So most of this particular talk will be predominantly based on my research activity at IIT Hyderabad. So I will try and avoid as much as possible not to be too technical, because if it gets too technical, it may be very difficult for some people to follow. But having said that, this is a technical presentation. We'll be having a lot of jargons, a lot of complex things. I try to make it as simple as possible. So these are all the baseline notes that I want to give. So I'm just going to share my screen. Please confirm whether you're able to see the full screen. Okay. All right. There you go.
Yes, sir, we can see your full screen. Yeah.
Yeah. So just one thing, not the presenter view. It should be a full screen that displays the whole slides. Just confirm whether you're seeing full screen or a presenter view.
Not
Okay.
the full screen. It's showing
Now
the.
it
Now
should
it's
be
okay.
fine. All right. So thank you. Anyway, so let's get started. So the talk is about laser technology at the frontier. So I just given a kind of a broad title because we are going to discuss about quite a few topics. So it's going to start from introducing you to the fiber optics, which is a very fascinating field. Not many people are aware of, and this is really having a lot of application. And of course, my work predominantly on fiber optics. So I take this the privilege to also introduce this topic to the audience. So we'll introduce about fiber optics, and I talk about the importance of communication. We are able to communicate just because we have these sorts of advanced communication existing now, thanks to fiber optic communication. Basically, we have all different modes of communication. End of the day, all these channels have to go in at some point of time to optical fiber, which is carrying the information from one place to other. Right, so communication, and then because this particular society is foundation is driven by a lot of experts who are really a big members in the Indian defense and space community. For example, Satish Reddy ji, who was actually one of the important pillar of Indian defense society, and also for a lot of people in the space is also involved in this. So we also talk about defense and space as well, right? So of course, I do quite a lot of research in space and defense as well. All right, so that's a fundamental outline. Now, so I want to introduce a little bit about, because this is open to many people across the country or even across the world. So I just want to take this opportunity to introduce IIT Hyderabad. Of course, many of you know. If not, so IIT Hyderabad is one of the premier institution, a second generation IIT we call. So we located at Kandi village, which is near about 30-40 kilometers from from Hyderabad. So this is our picture of a beautiful campus, but our campus is equally beautiful as this picture. And I have a lab which I call as Ultrafast Fiber Optics Lab. We say it is as UFO. We have a lot of people in our group, a lot of postdocs. Our postdocs are the people who complete PhD and continue the research, and a lot of PhDs who do the work for their PhD thesis, the doctoral thesis, and then a lot of master students, interns, people who are just completed their schools. They are also here some point of time, and then the students who are doing masters and undergrad, BTech, BE, etc., they're also involved in our activity. So primarily, I'm going to present the activity of my group. So these are the people who are actually currently existing with the group, and we are doing these things. So the primary focus, as I said, this is a technical conference and talk, and I will try to make it as simple as possible. So we do quite a few things in our research. I just want to introduce these topics, but I'm not going to take everything, and I will pick up few topics which is relevant to defense, space, and communication, and then I will do a deep dive in that, right? Yeah. So first is ultrafast fiber lasers. These are all nothing but pulse fiber lasers, which are very short durations. Lasers, we all heard quite a lot about it. These lasers are high intense laser source that's been useful for several applications. People use every day-to-day life. Will in one way or other we get to see a laser, get to see lasers, right? The lasers of all different kinds exist. And this is ultra-fast fiber lasers are lasers which are all very short, in the duration. They comes and goes in a very short scale, and 10 power of minus 14, 15, and that scale, right? This is very short duration pulse laser, they are called. And then we are doing quite a lot of work on developing new kind of a laser source, a laser source which is of spatially and temporally of different kind. So for that, you need to understand what actually gives you a laser. You wanted to know about how the laser forms, what are the various different effects happening in the laser. So you get, you can get various different laser sources, on-demand laser sources. Suppose I want lasers of this kind, how do I get it? Suppose I want a lasers for this application, how do I get it? For that, one should know the understanding about how laser works and what are the various components, various effects, physical effects, engineering challenges, we should know. So that is one part of it, because we are a laser developer team. We develop lasers for application. So that is one area. Now, AI is everywhere, isn't it? So we talk a lot about AI deeply into our life nowadays. There is no single day that we avoid ChatGPTs or any chatbot, right? So AI is everywhere. So and AI can be everywhere also. So even in photonics or engineering problems, everywhere AI are there. So what we do is, in one of our research projects, we integrate this AI, the artificial intelligence, into the AI system, so into the laser system, so that we leverage, the functionality of it. We now, about 15, 20 years before, we have seen a keypad phone, the small keypad phone, which has very limited functionality. Then came about the smartphones, the smartphone that comes with a lot of advantages, a lot of functionalities. It can do so many things now. We don't need a computer. Of course, for computing, we need a computer, but otherwise, for our day-to-day things, minimally computing things, our smartphones are good enough because they are smart. They do quite a lot of things. So what we want to do through our research is, how do we make a laser, which is a conventional laser, with a fixed configuration and solution? Can we leverage this AI and ML, and we come up with a smart laser which can do quite a few things? That's what one of our interesting area. So when it comes to space and defense application, of course, all these lasers will be useful for space and defense. But what we are quite extensively working on, or nearly about 60-70% of my group's workforce involved, is what is called as a coherent beam combination. I'll spend a lot of time, quite a substantial amount of time in this lecture for this particular topic, where we are generating high power lasers. The high power is going to have very lot of advantages for defense. I'm going to introduce about directed energy weapon. I happen to also heard the talk of Rajababu sir in the last week. It's a privilege to hear his talk. He has been one of my mentor, verbal wisher. So he also introduced about, in his talk, very briefly about the directed energy weapon. So that is also one of the area that we are interested in. Yeah. So sorry. And then the topic is about amplifiers, communication. We are a group. We work on optical fibers. Very soon, I'm going to introduce about the importance of optical fiber and optical fiber communication. We also we also work quite a lot in amplifiers. As the name suggests, amplifier, which means it amplifies the light, right? Which amplifies. But optical amplifier means it takes an input signal as an optical signal and then amplifies to a higher power. So that is optical amplifier. We have an electrical amplifier, RF amplifier, so many amplifiers. Okay, so this is an optical amplifier, which means it takes an optical signal and amplify it, right? So this is how my whole group research is. I'm going to talk about these topics. Let me take a laser pointer also. These are the areas that I'm going to discuss about. Okay, so there will be a brief introduction about fiber optics. I assume that many of you are not aware of. In order to follow the advanced topics, it is important that we also have to introduce this topic so that you get acquainted to the advanced topic. So as a teacher, I will be able to appreciate my lecture only if people can follow it. Okay, so for that reason, for the sake of completeness, I have introduced fiber optics, very basic thing, exciting thing. Okay, so especially if you are a school kids, if doing high school or higher secondary, I think this is for you, so you can follow these things pretty easily. And for our experienced people, senior scientists, it may be redundant, but there is something always to cheer about. Right. And then I introduce about ultrafast fiber lasers, then about high power lasers, why high power lasers are so important for defense and space application. Then I introduced to this particular technology, which is very futuristic. And to my opinion, this is going to be one of the very promising technology for high power lasers, which we are working quite extensively. So this is one area. And then about directed energy application, I said like not weapon as an application, because we do quite a few things based on directed energy, right? Not only the DW, which stands for directed energy weapon. We do quite a lot of other application, which is again come in the category of directed energy. We are directing the laser energy for something, right? And then the laser for different space, and then concludes, right? Please don't hesitate to come, ask questions if that is allowed, or if I'm overshooting the time, please let me know when to stop so that I can pace my talk accordingly. And if, since I'm only seeing the presenter view, if something goes wrong, I continue to speak. So please try to, if there is some issues, please, make sure that I'm getting that, right? So this is all about communication. This is what optical fibers, you see this optical fibers being connected. All these nice lines from here and there is nothing but an optical fiber, a small piece of, glass piece, which is in the micron level, is nothing but these optical fibers are. And we should be very thankful to those which actually enables all these things on the left side of you, right? All these things, the Twitter, the Instagram, the Facebook, the WhatsApp, TikTok, whatever you take, which depends on the internet, depend critically on this fiber optic communication, which means then optical fiber. This is essentially the optical fiber that takes this light signal, the modulated light signal, from one place to other. And then comes the local area network or whatever, the Wi-Fi's, the G's, all these things will come in. But predominantly, the optical fiber are the medium for carrying our information. From here to you, it's all happening through this optical fiber in some sense, right? So this is how, so okay. So this is a small video. It's not playing. Okay. Okay. So this is basically a small video that shows the globe where how is this optical communications is. The earlier picture was linear. This picture is kind of a globe that goes around. For some reason, it's not playing. Basically, you see this, the communications is happening all around it, both in the land as well as sea. But this is only showing sea, the subsea communication, but across the land from here to there, from Delhi to Telangana to there, here and there are optical fibers. You might have also seen this optical fiber laying across the road, on the sides of the road. Some people digging in, laying this optical fibers. So these are all nothing but a piece of glass, piece of fibers. All right. So communication is so important, isn't it? So I'm able to talk to you thanks to this also advanced technique. But people did communicate those days also, way back, hundreds and hundreds of years. But there exists very different kinds of communication. People use smoke, people use fire, people use horn. There are various means they do to communicate, right? People were living those days also. They were communicating. But what happened as the days goes on, we tend to become more advanced. We need more data. We need more faster communication. We want to send a lot of information, right? So this video, basically we are doing a video, an online video, VC, video conferencing. So this takes some more data, right? Simple audio signals will take less data, right? If you wanted to do a high definition, then you will going to take more data. So we become more data greedy. So we want more data to be sent in a faster rate, in the shortest time possible, all sorts of things. So the human evolution, as far as communication is concerned, is always in this way. There will be quiz. There will be always search for, much more faster ways of communicating things, or big communication things, right? More bandwidth I'm talking about. So, and so that's the reason why we have, 2G, 3G, 4G, 5G. And I also happened to see Professor Kiran Kuji was one of the top person in the 6G communication, who happened to be our faculty member in IITH Hyderabad, also has given a talk in this KIYE Foundation. So where he's a man of 6G. So you do the 6G. We are now talking about 5G. He's already a step ahead. He's now doing fantastic things in 6G communication. So probably 7G some point of time, or 8G, 9G. So things will always go on. Okay, the communication will always go on. So what the primary motivation behind all of this is that, so we want to have, faster communication, a very clear communication. There is no fidelity, no noise, no buffering, nothing. And then increased rate of transmission. You want to fast, more data has to be done, and longer distance. You don't want the communication to be limited to only short distance. We wanted to communicate beyond. Now people are talking about space communication and things like that. So these are basically the impetus, the quest that lead to more new technologies. So it all starts in those days, you have to do the communication because computer does not understand the continuous way of communicating. There's always a format, digital format. Okay, so is the communication also. This gentleman by name Morse, he came up with a modulation format like this, which means he represents A by dot and dash and B by dot and things like that. Okay, this is a way of modulating your signal. Suppose you want to write an apple, so this is how these things are modulated and sent, right? There is always modulation is important. How much data, how you modulate the data and send it for a communication, right? One of the most important, histories are always beautiful, histories are important. So I just thought, to excite, especially the school children to excite. So I thought I just brought in these slides. So the first, the biggest invention of the humankind as far as communication is concerned is basically this telephone. The telephone, basically you connected through a wire, you dial the number and things like that. So that's how it all started. People were very fine. It's possible because this is the invention that makes that it is possible to communicate someone beyond the line of sight, which means that I mean, if I can show some signal, I can show some fire. In that way, I can communicate, right? Suppose, for example, the sailors in this ship on the shore, there is a lighthouse which has some light, some signal. Okay, so the people who are sailing in the seas will understand that, and then they will reach it. It is a line of sight. There is a light there. Okay, if it is not in the line of sight, how do you do the communication? We need to find a way to do the communication, and that's where this telephones have now come. I mean, those days it has came. Right, so it primarily use about electrical signals and things like that. Then comes because it has a limited bandwidth. You cannot go more than certain limit. You can only do this many phone calls because the bandwidth limited and so on and so forth. And then comes the Bell photophone, so which uses optical signals. It uses an optical bandwidth which has larger bandwidth to work with. Right, I'm going a little bit fast so that I cover the advanced topic later on. So this is how US was in 1970s. This is a picture that I've taken from internet, by the way. So this is how the dense communication signals were there. You see how difficult it would be if you have a communications, the telephone lines were like this. It's so complicated. Even, first is limited in terms of bandwidth, and this is more complicated to work with even for technicians to fix something. So this is how it was. But now it all become a single piece of fiber. A fiber is good enough to do it. So what is the way forward? So let me ask this question. So how do we, mitigate this? How do we circumvent these sorts of complex, wires through some other means, right? So then for that question comes the light wave technology, which means use the light, the optical signals, basically, which carries a large bandwidth as a medium for communication, right? So this is how the typical basic communication system looks. If you can break down into pieces, it basically has a transmitter, which means I'm doing a transmission. It has to propagate through something. Yeah, there should be a medium to take it, move around, and then there will be a receiver which decodes it. I'm transmitting, it is propagating, and then it is receiving. So this is the very three pillars of the communication. It goes here, now it's a satellite, it goes all the way down there, and the receiver station, and then goes an optical fiber to decode this information. Right. So just for appreciation, advantages of optical communication over wires, the cables, the copper cable is this. If you wanted to do this, of course, the light travels at 2 by 3, the speed of light, because the light is propagated at the velocity of its speed. But when it propagates through a medium, it slows down, right? It slows down. All right. So if you use a copper wire, then you will be able to get close to about 100 megabytes per second. That's the speed that you're able to achieve. In a way, if you wanted to, qualitatively, if you can say, it is about 1,500 phone calls, and it's all qualitative, okay? It depends on the quality of the phone call also. So I'm not taking any reference to that. And 2 TV channels, and then, for references, 2 Bibles per second. If you digitize this Bible and then send it, you can do it about 2 Bible per second. If you have a coaxial cable, this bigger cable, so you are able to do it order of magnitude higher, about 15,000 phone calls. But imagine about this is not sufficient. This is not okay. So for that, people have looked into optical means of doing through the light wave technology, where we can take about 50 terabytes per second and so on. I think these are just a reference I'm trying to give you, right? About 8.78 billion phone calls. Imagine. So that's what currently happening. So it's all possible through the light wave technology. All right. So now it means that light wave technology have a bigger bandwidth to work with. So it is good all sense, but there should be a medium, right? Of course, light can travel. If you take a torchlight, a pocket laser, for example, if you send it, the light can travel. But what happens when the light can travel? It goes through a lot of disturbances, the atmospheric disturbance, and light always travels straight line. So it becomes of side communication from one point to other. If you wanted to send the light through some other way, you have to guide the light to that particular destination, which is not always possible if you don't have a medium to do it, right? And if it is not medium, if you say, it's easy to taper also, right? Your light is going, so somebody will say, oh, there's a light going, there is something happening, let me go on poke it, let me go on and then do something about it, which is again not okay. So we need to have a medium, and that medium is nothing but an optical fiber. So that leads to what is called as a fiber optics, right? The light is being guided through an optical fiber, okay? So because it is light, so it is optics, and there is a fiber that is carrying, and that becomes an optical fiber. That means the field is called as a fiber optics, right? So yeah. So anyway, I did explain over the previous slide. So an optical fiber, how it looks then? The nice. So I do convince that optical fiber is fantastic. Then how it looks? So how it how it is physically? So it just consists of, it's nothing but a piece of glass. Glass is a transparent medium. It can send the light across, right? So it's a piece of glass that has a core and a cladding. Okay, so both are glass only, both are pure form of glass where light can propagate. But we should have a structure like core and cladding, which is this core, this is core and cladding. Excuse me. And this is core and this is cladding. Okay, so the light will travel in the core very nicely by the phenomena of what is called as total internal reflection. Okay, so when the light goes in, this light get reflected back into the medium, because the reason is that this is another medium. Of course, both are glass, but they are different in terms of refractive index. Okay, light knows only the refractive index. Okay, when it goes in, it sees that although both are glass, but the refractive index is purposefully modified so that this will be of higher refractive index, this will be of slightly lower refractive index. So the light sees an interface between denser to rarer medium. So whenever the light goes from one medium to other, it either reflect. Okay, so what happens is, if you're able to meet a condition which we call as a total internal reflection that comes from the Snell's law, the light can be trapped back into the fiber, and this light can propagate. It's a simple way of giving a ray optics context to this light propagation. So the light is propagate in this way, and then you can carry the light. Okay, since it's a waveguide, right? Like a pipe, water pipe. Pour a pipe of water into the pipe, the PVC pipe. So the light will go, the water will go, and then you can channelize this. That's what we are doing. The piping, the plumbers will do the piping in our home, so they can carry this light here and there, the water here and there in a nice way. So the same is possible through the optical fiber. That's why we can break this issue of line of sight. We can take the light to anywhere. Right? This is what I was trying to say. The light goes inside like this. So there are ways. There are different ways of optical fiber. One is the based on the refractive index profile. This is a high refractive index, which is called here also. There is a low refractive index. Why we are having it? We are having it because we wanted to support the guiding mechanism. We want the light to propagate inside. Okay, based on the refractive index, whether it is changing as a step or gradually changing, there can be two different kinds. Okay, let's assume that there's a whole set of reasons why we have to think about this, but for this particular lecture, this is sufficient. Based on the refractive index, the optical fiber can be of a different kind. Okay, so the question comes also, why the light can, this is a lower refractive index, this is a higher refractive index. I was just telling that the refractive index difference is there, then it should be sufficient. Why would bother to have a cladding? Right? So the reason is that it's for the same. I mean, it's also to support the guiding mechanism, because the refractive index contrast matters also. And further, if you're exposing your guiding medium, even a small thing, suppose if you're holding the fiber, a fingerprint even will give a local refractive index change, and that affects your guiding mechanism. That's why we need to have, right? So this is what the optical fiber, the light propagation would look like. So we need a medium for light. We need a medium for propagation, because we don't want the light to be exposed to the free space, and we need a medium, and that medium is actually an optical fiber, because it ideally can guide the light through it, right? So the mechanism, I mean, of total internal reflection is pretty straightforward. So I mean, this is one representation. When you put the light there, you see this, the light is coming. This experiments would have done in the school, right? The light will reflect back and forth, and then you see this light get trapped. So this is what is a simple example of classroom level demonstration of total internal reflection. So this is what I was trying to say. When you inject the light, it reflects back. There is a critical angle where the light will traverse the interface, but if there is any angle greater than that, the light will totally reflect it back, and then it sees another interface. Like that it goes. Okay, so this is our simple example. Right, for an appreciation, if 1 micron is this, okay, the human hair is this, okay, the optical fiber would be of this kind. If the human hair is of this size, this 1 micron is relevant to it, the optical fiber will be looking that small is the fiber. But this is not a simple fiber. The fiber have to be supported by so many other structure, because very glass piece, right? When you bend it, it will break into pieces. It has to be supported by several other supporting structures. If it is normal, in the ground-based fiber. But if it is a sea-based, because it has to go through a rough sea, there are a lot of disturbance and turbulence and things like that. So it has to have additional supporting, right? So the advantages is that, I mean, the optical fiber can do a job of this big an optical of a copper cable, just for an appreciation. If you want to do the same sort of a
Excuse me,
data,
sir.
yeah. Yes.
Sir, we will be starting questions after 5 minutes if it's okay. Can you
Oh, okay.
ask?
Okay. So then I have to move a little faster then. So maybe 10 minutes should be okay? No?
Yeah, thank you, sir.
All right. Okay.
Yeah, sir,
Fine
it's okay.
then. Yeah. So, all right. So I'm just wanted to summarize that there are a whole lot of advantages of optical fiber communication compared to a copper cable. Okay. Let's understand that. Now, the next topic is basically fiber lasers. Now, optical fiber, you can use it as, as a simple optical fiber. You can use it for communication, taking signal from one place to other and all different sort of a thing. But these are all such a nice medium where we are moving from communication to other topic, which is a fiber laser, which is actually an important topic that I want to dive deep into it. So now the second sort of, optical fibers are fantastic in terms of carrying the light. Now the question is, can we make a laser out of it? We heard about lasers, right? Lasers of various different kinds are there. Solid laser, which means that the medium that gives us the laser is actually a solid. A liquid laser, as a liquid is actually an active medium. Gas laser, and also different kinds of this. A fiber laser is nothing but a solid state laser where the active medium is itself a fiber, okay? Which means that a laser requires an active medium where energy has been taken and amplified, and then it goes into several amplification and becomes a laser, okay? This is a transition from a low power, like a low coherence light source to a high coherent, high intense laser source. This is a process that is involved. But people use all different kinds of lasing medium. But what we are going to see is that optical fiber, which has a core and cladding, can be also used as an active medium so that it can give a laser. Why one have to bother about going for a fiber laser when there is already lasers of all different kinds exist? The reason is that this is a guided laser, okay? If you see this normal lasers, free space lasers, which consist of lot of lenses, mirror, prisms, and so complex things. But this is actually a light is guided inside. It is possible for us to get a guided laser, which is having a very high beam quality, as well as we don't need to do this alignments. People works in optics know it is very challenging to do the alignment. Okay, we don't need to do it. It's a kind of a plug and play sort of a system. And heat management is a very important thing here. In any laser system, we have to have a cooling system. In a normal free space lasers where the active medium is solid, so what happens is in a whole heat energy is heat is there located at one place. So thermal management is tricky and challenging. So in the fiber where it is like a fiber, the whole laser length of the fiber can be used as a it's the volume to surface ratio is high, so the heat dissipation is easier. So we need not to worry too much about the cooling system. Of course, if you go for high power, we need to have it. Okay, that's one thing. So as far as early development is concerned, the fiber laser was actually invented at the same time, almost same time as as a normal lasers, but it has to wait for quite a lot of time, close to about 20-25 years. It's just because people didn't find a suitable optical fiber a medium to do this fiber laser. That's why the delay. But actual things started from the same time as us. Now is the point. So I was trying to say this fiber laser is fantastic. And this fiber laser has actually brought a laser industrial revolution, second laser industrial revolution. Original one is basically a laser diode at 1980. So the second laser revolution predominantly is held by actually the fiber lasers, because it has penetrated almost every market. If you think about marking, this is Chaminar sort of a thing. And then if it is about material processing, micro machining, you have a LIDAR. For autonomous vehicle, you have it. You have this laser-based weapons, a directed energy weapon. You see this laser been everywhere, right? So, and fiber laser is actually fantastic to it. This is how a fiber laser looks. And you have pump a light, then the light get trapped in, and then it gets amplified multiple times and sufficiently amplified, and then it comes off. This is a very simple way of explaining the fiber lasers. But what is important is a pulse laser. Pulse laser means if a torchlight, if you shine the torchlight, if you turn it on, you get the energy all the time, right? But what happens is if you're just chopping this light energy, if you wanted to take it on and off, then you have a burst of energy at the short time. Just like if you let the water dam open the shutter, the water will flow continuously. Suppose if you chop it, close the shutter, open and drop, then you see the huge amount of energy coming out. In short time, huge amount of energy comes. That is called pulse shortening. So because this kind of pulse lasers are very useful at many very different applications, because if for micro machining or if you want a very high energy at the short time, so we'll be able to see those applications there. So based on this kind of a nature of application, one have to go for a various different kind of a laser architecture. So this is one single representation of the usefulness of the fiber lasers. You see the security and defense, the long distance transmission and DEWs and things like that. People in medical industries use dentistry, surgical, kidney stone lithotripsy and things like that. And engineering, and where people use for manufacturing and micro machining and sensing and so on and so forth. There are quite a lot of application. Right, I'm moving on a little faster. So what we do in our lab, I'm into the last 5 minutes probably. So what we do in our lab, we do quite a lot of things. We basically develop the fiber laser, all about fibers. This is optical fiber. These are the various different components that is involved in the fiber laser. We pump the light optically and then combine it. Then this does an amplification and then goes into the fiber. This is called, satural absorber, where the light, I told you, right, shutter sort of a thing. The light gets chopped here, and then you get a nice pulse laser source. So this is about fiber laser, pulse laser fiber lasers, right? And then what we do is interesting about this. The fiber laser gives various different kinds of states, various different kind of lasing states. But finding them is very challenging because we do not know in a fiber laser cavity where are they existing. Usually people will do the trial and error. So what we are trying to do is we are now we're working on what is called as a smart laser, which means that where the AI is involved in it, which means there exists certain configuration that gives you a certain application, certain laser regime, but unfortunately it is not accessible to us. It's very challenging to find it. What we do is we develop an algorithm, educate that algorithm that this is what I'm actually looking for. Can you please traverse the space, look into the space and identify and give the exact parameters that is required to get this desired output. So this is basically involving algorithm, the AI algorithm into it, and get a very desired output, because there are so many useful things exist, but we do not know where are they. So in order to get it, we need to know how to get it. So it's always very challenging for us to locate it. So now AI intelligent algorithms are coming into play. So this is what the smart fiber lasers we are working on. We have several results. Now it's about defense applications. So defense applications for very long distance, we need to have a very high power. I introduced you to fiber lasers, but what happens is a single fiber laser cannot give you that much of power because if one laser cannot handle that much power. So there are a lot of challenges in it because the thermal management issue, even if you're managing it, the beam quality is not good and so many other things. So people look for various different kinds of ways to get the fiber lasers, high power fiber lasers. These are the applications. In fact, this one got a Nobel Prize. So in fact, the person who invented this particular Nobel Prize is going to come December to IIT Hyderabad for a conference. So various different sorts of technologies were there at different ages. What we are looking is basically laser beam combination, which means we are combining multiple lasers like this to get a very high power. It is like, many lasers have been combined constructively. Okay, so you get a very high power. So that actually you want a high power, and since single laser cannot give you wanted to combine multiple lasers to get that high power. So this is the simple way. So what we are working on in this particular niche technology is that we work on both destruction and construction. Okay, so it's always two-phase, destruction and construction. So when it comes to a destructive application, direct energy weapon use the laser energy to basically take down any object, a drone or anything. So we are working some part of it. Of course, we are not entirely working. We do some part of research in this. Being in academia, we only can do some part of the research, not the entire system. On the constructive part, we are working on manufacturing, because now 3D printing is a laser-based 3D printing, which means the manufacturing. Use a laser energy to do some sort of a manufacturing, additive manufacturing, subtractive manufacturing, so many things. We also work on this base, coherent beam combining base technology for manufacturing application. The other two is about power beaming. We wanted to send this laser power to a distant object. Suppose assume that there is a target, there is not a target, there is a drone or anything which is very fast. So we wanted to send the energy optically to it. There is, because the drone works based on the battery. Suppose if the battery life is not enough for the flying time, you wanted to do it, you cannot tether it, you cannot give a wire to it, right? It's not possible. So how do we do it remotely, wirelessly? So that is one thing. And we also worked on long distance fiber free space communication. So I quickly introduce in another 2-3 minutes as maximum. This is a representative slide. So this is what I call as a directed energy. We work in all of this. Okay, so feel free to ask questions on this, maybe in the interactive time. Right, this is where, suppose if you have a target, this is a laser source, there is a target somewhere hovering over, so you basically use this directed energy, laser energy to take it down, right? And this is another one where we have use the laser energy to do some sort of a manufacturing, additive manufacturing, precision manufacturing, things like that. And this is one representative picture where there is a drone. The drone is being powered remotely here. And this is like intersatellite, long distance free space communication. So this is also one area we just started. All right, so this is a brief explanation about, I already said. So this is what is about coherent beam combining. Basically, you have one laser, and that laser has been split and amplified, and so many processes involved, and then combine them. If you are able to match their phase, because they are traveling slightly different, so the path difference are different, there will be a path difference. So we wanted to make sure that they are all combining. Assume this is a sine wave, this is a sine wave, this is a sine wave. They all only constructively interfere if the peak and the valley matches exactly, right? So if they don't match, then they destructively interfere, then you get something else. So we want something like this, a simulation results. Basically, we wanted to make sure that they are all in phase. How do? We basically sense it from here, we'll give it back to a controller. There are actuators. The actuator will compensate for the path difference or the phase difference, whatever it is. So this is how we get. So what we wanted to get at the end, we wanted to get a very high energy, high power density at the target. So this is what is our application, right? So how do? We basically we built turbulence, because the light have to go through an atmosphere, right? When the light goes through atmosphere, it's subject to a lot of effects, atmospheric effects, scintillation, turbulence, beam wandering, and so many things. We do this all sort of a test in the lab, in our turbulence chamber, where we subject the light beam propagation, and we do the studies, what different sort of an effects are there, how do we sense it, and how do we compensate it, and things like that. Okay. And then this is another application which I was talking about, the manufacturing, the similar sort of technology. What we do is we basically, you control, instead of getting very high power density at the target, what we wanted to do we wanted to shape the beam here. We wanted to get all different kind of shapes, because the shape is really very important for manufacturing. We don't want a Gaussian beam which has very high intensity here and then a low intensity here, because that interact with the material and create a temperature gradient, because high intensity will create a much hotter point, a low intensity will create a weaker hot point. So there is a temperature gradient between these two places, and that is not desirable. Okay, so how do we engineer the beam in such a way that best matches with our manufacturing requirements? So that is one laser-based industrial application that we're doing. Right, and then comes it's a power beaming. So we want, there is a target, then we wanted to optically transfer the power to it. It's not possible for a physical infrastructure. Suppose if we want a disaster hit place, some mountains or somewhere, we wanted to do it. Now, for example, there is a flood everywhere. Suppose there is a remote place that doesn't really have connectivity, for example, how do you send this? It's not possible to lay down a wire. So how do we do it? If you are able to provide them with the right sort of infrastructure at them, we are able to remotely power them. So also it's a very defense application, but it has a lot of civilian application also, right? So the idea is that you transfer the power. So these are all some, very early stage of research. And since this talk will be in public, so I am avoid to give the technical details. So we do quite a lot of research in this, right? And then the last thing is about wireless optical fiber, fiber optic communication, wireless communication. What we do is basically this coherent beam combinations, basically. There are free space communication that is possible. When a light is sent, you have a detector, that's all. When the light is detected, the communication is done. But what happens is it has a lot of challenges in it, because the light have to go through atmosphere. There are the light will beam divergence will be there. There will be a loss, alignment issues, and we need to have a larger receiver. So can we have one single system that will be able to take care of all these drawbacks? And we see this, there are reports also, and we are also working on it. It's possible for us to use this tile fiber array for atmospheric turbulence free communication. So that is one area that we are working on, right? So in the interest of the time, just to maximize the interaction, I conclude now. So I introduced to you about the fiber optic communication and as well as the ultrafast fiber laser, how the fundamental and applied interest of it, the hyper fiber lasers for defense, space technologies, and the most important part is about the coherent beam combination, where I introduced some of our results on direct energy application pertaining to weapons, power beaming, manufacturing, and communications. So there are a lot of opportunities to work. I'm always looking for highly motivated students, interns to join in our group. And this is, all these things is done by these people. So basically, I'm just giving a voiceover to their research. And these are all the funding agencies that supported our research. I'm done, and thank you very much. Sorry, I have to rush because I planned for 1 hour. I was not knowing about, this, we have to limit to 40 minutes or
Thank you so
something.
much, sir. I actually really apologize for disturbing your presentation earlier. Thank you for
Right, no
accommodating the
problem.
time limit and sharing such an informative and inspiring session, sir. Thank you so much.
You're welcome.
And I'm
Thank
sure
you.
everyone watching has learned something new today. Now it's time for the interactive questions. So participants, it's your moment. So please post your questions, short, clear, and relevant to the topic. And with your permission, sir, we will now have a few questions from the live audience. Is it okay?
Right, absolutely.
Yeah, okay, sir. So, sir, the first question is, uh, sir, can we transfer an information through light or a laser? Li-Fi. But why are we not using this technology?
I'm not getting the question. Can we transfer light? I'm not getting it.
Uh, he's saying that can we transfer an information through light or laser? But why are we not using this technology?
No, we are using this technology. We basically use this technology only. So suppose I'm speaking, okay, some analog signals. So this will be encoded in a digital stream, and this has been carried by basically in an optical way, only in optical fiber. So in a bit stream, let's say a very simple way. So we basically digitize in the binary format. Let's assume. So it's become zeros, one zeros, and zeros, right? So in optical communication, zero means a no light, right? And one means a light is there. So if you have suppose I want to send a digital 010, okay, I will basically going to send in my optical fiber, highly modulated signal. 0 means no light, 1 means there is a light, and 0 means no light, and things like that. We are actually doing this communication through light only, okay? But local area communication, Wi-Fi and all in a different band, so that is different. But what I was talking about is optical fiber communication. Essentially, light is being sent into the optical fiber.
Thank you, sir, for making it easy to understand for them. Sir, the next question is, what is the most exciting real-world applications or ultra-fast laser the student should know about?
Oh yeah, okay. So the most, actually, it's bit vague to say. There are quite a lot of applications, as I said. Like for example, if it is defense application, it all depends upon the people. What they are looking for. Applications are. I cannot say this is the most. No, it cannot. Defense application can be very important at this point of moment, looking at the geopolitical situation. But on the other hand, ultrafast lasers are also being used in biomedical application, for surgical procedures and therapeutic applications. And for example, for manufacturing, we need to have materials, right? We need to have component systems and so many other things. So I'm afraid and refrain from saying that this is the most important application, but rather I would say that applications are infinite, okay? And yeah, lasers and lights and ultrafast lasers have been useful for a lot of applications. So I cannot say that this is the most important application. Yeah, it depends on the people. I'm not able to hear you. I'm not able to hear you. Please come again. Now it's fine. Now it's fine.
Okay. So there is a student coordinator who would like to ask a question to you.
Yes.
Yeah, Saharsha, can you please open your video?
Good evening, sir. I am Harsha, fourth year
Harsha.
student.
Harsha,
Sir,
please go
with
on.
rapid advancements in integrated phonetics and silicon phonetics, do you think they will eventually replace conventional optical systems, or both will technologies continue to complement each other?
Yeah, I mean, I would say that the advancement is in this direction of integrated. We want everything to be in a small chip. Of course, there is something called swap, size, weight, and power, right? So people want everything to be in a very ruggedized, in a small manner, so that it is very compact, efficient. Okay, so of course there can be application where this integrated photonic system, PICs, and things like that would be very useful, very handy, and it is needed also, where the requirement is more compact system and things like that, very power efficient, energy efficient systems, and for data centers and things like that. But when it comes to a directed energy application where we have to deal about kilowatt of power, I mean, I don't think this integrated photonic system can come handy for those things. So it is going to complement each other. But I do agree there is an increasing interest in integrated photonic system, making everything so compact because people don't want a big system on a table. That is true. But PICs and integrated system are not going to replace every big systems.
Thank you, sir.
So there is one more question.
Right.
Why are optical fibers preferred over conventional communication media in modern communication systems?
Oh yeah, so because the first thing is why optical fiber. I should see why optical fiber is just because it's cheap. Okay, it does the job. The cost of making 1 kilometer of single mode fiber is damn cheap nowadays. Okay, and but if you're going for other modes of copper cable, for example, or for any other communication for that matter, it is the cost per length is expensive. That's one thing. It's in fact the economy that drives everything, right? That's one thing. Another thing is the optical bandwidth is very high, and you have to look for a medium that basically accommodate that large bandwidth. So the optical fiber can only do it, right? And it is why optical fiber is also is just because you can bend it. It's ductile, malleable. So many material chemists will say. So this can guide the light nicely. First, you want a medium that can guide it, and you want that guiding should be very proper, minimally lossy, no more loss, minimally lossy, and then it has to have a right bandwidth. And top of it has to be cheap enough. It should be cost effective. Imagine about a situation that optical fiber have to be made out of a gold. Think about a weird situation. The data rate would be per month would be easily about in lakhs probably. So it has to be very cheap as well. So optical fiber is preferred for this reason. It's cheap and do the job in the best way possible.
Thank you, sir, for explaining it clearly. I hope they will understand. The next question is, sir, that what are the biggest challenges researchers are trying to solve in our fiber optic technology today?
The biggest challenges are fiber optic technology is that, again, if I talk in terms of power, okay, a single fiber, for example, cannot accommodate more power, okay, because it's a single mode fiber, the power density is limited because when it crosses certain limit, the thermal damage can happen, the material damage can happen. So the single mode fibers is hitting a limit, okay, it's hitting a limit. This is where it can go up to. Beyond that, I think it's a challenge. So that's what now people are looking for, a multi-mode fiber, okay, which means that the fiber can support more modes, a bigger core, more power it can handle. And in fact, we do quite a lot of work in communication. We call it as a spatio-temporal communication. Okay, so basically, bigger pardon, it's space division multiplexing. Okay, which means that a bigger core, each core a bigger core can support more modes. You can think of each mode as one channel, one single mode, so that we can multiply the information carrying capacity. Suppose we have 2-mode fiber, very simple layman example, 2-mode fiber. The 2-mode fiber can potentially replace 2 single-mode fiber, right? Okay, so you have to, of course, this complexity is there. You have to manage the modes and other things, but people are looking into this direction. The other one is about hollow core fiber. There is another interesting avenue where people are using hollow core fiber, where there is no real core in terms of physically. So people are now guiding light through this. This is another advancement. Okay, and the other challenges are about fibers for various different wavelengths. Now we are predominantly talking about NIR, near IR, 1 micron, 1.5 micron, 2 micron. Suppose, if you're looking for application in for example, mid IR and far mid IR and things like that, then we have to come up with various different kind of whole fiber optic technology for that. So there are works in this direction. Okay, so I think these are the things that I can immediately think of. But as like any research, people will always push their limits. Right? We are now, we want to push the limit. So there are various avenues, high power, more data rate, various different wavelengths and sensors, for example. People are working, but a lot of people in Indian community works on sensors, fiber optics based sensors, because they're very good, very accurate, very efficient and cheap also. So people are working in this directions also. Yeah.
Thank you, sir. So, they're asking that can fiber optics play a significant role in space communication in the future?
Everything is, I would say that everything happening in land is happening now in space. Okay, space is a new kingdom, new avenue. Okay, so I don't see that free space communication is a different thing. You send the light through a free space. Okay, fiber optic communication, you send the light through the fiber. Okay, now space is become a new world now. You see this moon mission, you see this Mars mission by Elon Musk and things like that. So when people are now looking for a new territory, new planet to live, if that become ever reality, whatever happening in the land whatever happening now here will also be there. So as far as communication is concerned, I don't think so. Of course, here and there, fiber optics will come in play to do some sort of a thing. But otherwise, by and large, communication wise, it's only going to be free space. But if the situation ever comes in where life becomes possible and more things happen in the space, then fiber optic technology, like any other technology for that matter, will also play a prime role.
Sure, sir. So, what are the current limitations in ultrafast laser technology, and how can they be overcome?
Okay, so what are ultrafast technology? So again, I'll come down to about ultrafast. The width of the pulse. How sharp the pulse can be. Again, it's femtosecond. Now there is a lot of research about attosecond. You want to minimize the pulse width so that you can get more peak power. There is one direction in which people wanted to do that sort of a thing. More shorter, make it more shorter to the high peak power, and that is one thing. And then about the faster pulses, controllable pulse repetition rate. Pulse repetition rate means when the pulse comes like a train of pulses, right? Then how do you control this train of pulses? How we get more peak power and things like that, and more of work in the application domain, like rather than in the source itself. Source is all about getting high peak power and much shorter pulses and more controllable pulses with more spatial and temporal features controllable. But by and large, it's all on the application side of it. Yeah. So where we can use this in a better way. So, for example, in one of my talk, one of my lecture, slide, I was talking about manufacturing. Manufacturing. We did 3D printing and additive manufacturing. How do you control the spatial profile, temporal profile, and things like that, so that the power delivery is optimized? So these are also the direction where ultrafast fiber laser technology is going ahead.
Okay, thank you, sir. This is the last question from one of the participants. What skills should ECE and physics students develop to build a career in photonics and laser technology?
It is a very interesting question. Photonics is one of the very rare and very nice field where you'll see this engineering, and especially, I mean, I'm not limiting to EC. Okay, of course, EC have a greater role to play. In many of the institute, the photonics work is predominantly driven by electrical and communication engineers. Okay, but I'm not limiting to EC, but photonics is a very interesting interdisciplinary research domain where the biggest drivers are physics and electrical engineers and communication engineers. But even it is quite interdisciplinary that people from mechanical, people from other areas will also can actively engage in. But when it comes to EC and physics, yes, physics will bring in the fundamental aspects of light propagation, controls, and things like that. Whereas communication brings in the engineering challenges of it, the signal processing, the DSPs, the control signals, and things like that. So, I mean, I would say photonics is a very nice, interesting field. It's very balanced and sandwiched between these two particular thing. So where one can cherish, engineers will learn about the optics, the basics of optics, the light, lasers, and things like that. Whereas the laser scientists or basic physicists, for example, can work together to learn about signal processing and then control and various aspects of engineering as well, right? So I would say that this is a very nice interdisciplinary research, and both can play a very bigger role in photonics.
Thank you so much, sir, for patiently answering all our questions and interacting with the students today. Now, the final part of today's program, I would like to invite our coordinator, Ms. Mohita, to deliver the vote of thanks. Mohita, the virtual stage is all yours.
Thank you.
Thank you, Rahitya. Good evening, sir, and good evening, everyone. I'm Mohita, one of the student coordinator at KIYE Foundation. It is my immense honor and privilege to deliver the vote of thanks for today's session. On behalf of KIYE Foundation, I extend our heartfelt gratitude to our esteemed speaker, Dr. Nithyanandan Kanagaraj, Assistant Professor, Department of Physics, for delivering such an insightful and inspiring session. Sir, your enlightening talk has given us a deeper understanding of the fascinating world of fiber optics, ultrafast lasers, artificial intelligence in photonics, and emerging optical technologies. This session has truly inspired all of us to think beyond boundaries and explore the limitless possibilities of research and innovation. Thank you, sir, for taking the time to share your valuable knowledge, motivating us with your remarkable journey, and patiently addressing our questions. Your words have encouraged us to pursue your excellence with dedication and a spirit of innovation. And your passion for research and innovation has shown us that science is not just about discovering new knowledge, but also creating solutions that benefit society. I would also like to express my sincere gratitude to our respected dignitaries, mentors, and the entire organizing team, and everyone who worked beyond the scenes to make this session more success. To all the participants, thank you for your enthusiastic presence and active participation. Your eagerness to learn and active engagement made the sessions truly meaningful and interactive. I believe you will never stop learning, never stop innovating, and never stop exploring. Always work towards building a stronger and self-reliant India. As we conclude, let us carry forward the inspiration we have gained today. May you continue to learn, explore, innovate, and contribute to India's future of science and technology. Once again, I thank Dr. Nithyanandan Kanagaraj Garu for sharing your valuable knowledge and joining us today. Thank you, everyone, for joining us and making this session more informative. Jai Hind.
Thank you. As we have come to the end of today's S-Talks Lecture 19, I would like to express our heartfelt gratitude to Dr. Nithyanandan Kanagaraj Garu for sharing his valuable knowledge, inspiring research journey, and wonderful insights into the world of photonics and advanced technologies. Your words have reminded us that every great innovation truly begins with curiosity, hard work, and courage to keep learning. Sir, thank you once again, sir. The response from the audience was actually fantastic. If your schedule permits, we would like to host you for another session in September, October at your convenience, sir.
Yeah, we can do that.
Okay.
Sure.
Thank you, sir. And
thank you.
I would also like to thank every student, faculty member, researcher, and participant who have joined us today and made this session even more meaningful through your enthusiasm and interaction. If you enjoyed today's lecture, don't forget to stay connected with the KIYE Foundation by subscribing to our channel and following us on WhatsApp, Instagram, and LinkedIn. We have many more exciting sessions waiting for you. And until we meet again in the next X Talks lecture, keep learning, keep asking questions, keep innovating, and keep believing that your ideas can actually help build a stronger and a better India. This is Rahitya signing off for tonight. Thank you everyone. Jai Hind.